In this video, we're going to give an overview of the periodic table, specifically looking at how intentionally the periodic table was designed to group elements based on similarities in reactivity. And a lot of that similarity in reactivity comes from similarities in their electronic structure, how many valence electrons they have, how many core electrons they have, how the electrons are distributed in the atom contributes to their similarities in reactivity. So just as a quick overview, we kind of went through this in one of the earlier units early in the course. But just as a reminder, all of the columns of the periodic tables are called groups. The rows are called periods, right? And in that early unit, I think it was unit 2, we went through, just the basics of the periodic table. What's the atomic number, atomic mass, the symbols, the names, right? Now we want to go into more depth of how the periodic table is arranged and how similar the electronic structures are of elements in similar groups and periods. So what you'll notice on most periodic tables are these labels underneath the groups, right? All the groups have at the top generally just a number 1 through 18, right? Just as signifying that there's 18 groups in the periodic table. But then each group will have another identifier, right? So this little Roman numeral with the A underneath it, right? You can see it here, here, and here. If it's too small, then try to pull up another periodic table or something that you can follow along with. But so like right here under group 13, you'll see a label that says 3A, right? In some cases, it'll be a Roman numeral. In other cases, they'll just put the number, right? 3A. But what does that 3A actually mean, right? What does it correspond to? Well, it actually corresponds to the valence electrons that are in the atoms in that group. Right. So if we take boron, for example, right, let's take boron. It's at the top of group 3A. Right. In fact, let me label this group 3A. Right. And if we take boron and look at its electron configuration, boron has the following electron configuration: helium to signify its core electrons, and 2s2, 2p1. Right. So from this, right, we see that boron has 3 valence electrons. Right. What about aluminum? Right. Aluminum's just below boron. Right. Let's look at aluminum's electron configuration. It has the electron configuration neon, 3s2, 3p1. Right. So both of these atoms have 3 valence electrons. Right. So these 3 valence electrons are a staple of all of the atoms that are in this group, right? Everything from boron to gallium to thallium, indium, right? All of these elements, all these atoms will have 3 valence electrons, right? And that puts them in group 3A, right? So let's look at group 7A. Right, so group 7A is here, the halogens, right? Fluorine, chlorine, bromine, right? So let's look at group 7A. And let's take fluorine, for example, right? So fluorine would have the following electron configuration: helium as its core electrons, 2s2, 2p5, right? So here we have 7 valence electrons for fluorine. And let's go to iodine. Right, so iodine's all the way down here, right? So iodine has the electron configuration of krypton, right, as its core, as its noble gas to signify the core electrons. And then from there you have 5s2, 4d10, and 5p5. Now, we discussed in the previous video that if you have a full D shell, then you don't count those electrons as valence electrons, right? So those 10 valence electrons in the D shell would not count. So we only have 7 valence electrons here for iodine, right? Putting it in group 7A. So that means that these electrons will have, or these atoms will have similar reactivity because they have the same amount of valence electrons, right? They'll form similar molecules, they'll form similar bonds, they'll have similar properties because of the similarity in their valence electrons, right? And a lot of these groups are dictated by where the valence electrons are located, and how that signifies throughout throughout their reactivity, or defines their properties. So a few things I want to point out here. There's a large delineation, more of a surface level delineation of the periodic table of main group elements versus other elements. And what we mean by main group is anything that's in group 1A to 8A, right? So that's 1A, 2A, 3A, 4A, 5A, right? So basically everything that's not the transition metals and the lanthanides and actinides, right? That's all considered main group chemistry. And there's a large, even though they represent, even though they only represent a portion of the periodic table, they represent a lot of really important chemistry. So if you have to take organic chemistry is primarily the chemistry of carbon and hydrogen, right? Hydrocarbons. But a lot of it is dealing with the main group elements. So you'll see a lot of compounds that have nitrogens, oxygens, different halogens in them, right? So really the main group represents a lot of important elements in chemistry. And everything else, these ones here, 3B down to 2B, and we'll talk about that designation in just a second, are the transition metals, the lanthanides, the actinides, right? So now let's talk about the transition metals series. So that's everything that exists here, right? Everyone's that's group label has a B in it there. Those are the transition metals. And the transition metals are characterized by having valence d electrons, right? So let me go to a different slide here and start for transition metals. And let's look at a few of the electron configurations for some transition metals, right? So let's look at vanadium, right? So vanadium has the following electron configuration: argon, 4s2, 3d3, right? So if we look at where vanadium is on the periodic table, right, we see vanadium right here, right? 23 total electrons. So we've accounted for all of those. And what you'll notice, we got 5 total valence electrons, but we have electrons that are in the D shell, right? So we got some valence D electrons. Vanadium is a transition metal, and they're always characterized by electrons being in these D shells, right? Also iron. Let's look at the electron configuration for iron. Argon, 4s2, 3d6, right? So iron is going to have 8 valence electrons, 6 in the 3d, right? So again, these transition metals are characterized by having these valence d electrons, right? Okay, so the other groups of the periodic table that I want to highlight are the lanthanides and actinides. So you'll notice that that's these 2 rows that break off, or I should say these 2 periods that break off of the periodic table, right? Their position in the periodic table, is right here, right? So like for the lanthanides, they occur between barium and hafnium. You can see that their atomic numbers fill in this gap between barium at 56 and hafnium at 72, right? The lanthanides fill in that gap. Same thing here with the actinides, right? They fill in that gap between radium and rutherfordium from 88 to 104, right? So they fill in that gap in the periodic table, and they're broken off to be placed at the bottom. And they're characterized by having, for the lanthanides, having valence 4f electrons, and for the actinides, having valence 5f electrons. So let's look at some examples, right? So for the lanthanides, right, so one of the lanthanides is europium, which has the chemical symbol Eu. And its electron configuration is xenon for its core electrons, 6s2, 4f7, right? So here we have valence 4f electrons, right? So you have 9 valence electrons total, and 7 of those valence electrons are in the 4f subshell. And let's look at some actinides, or let's look at least one example of an actinide. Actinides. Right, so for the actinides, let's look at americium, which has a chemical symbol of Am. So that's going to have an electron configuration of radon for the noble gas core electrons, and other electrons placed in the 7s, 2 in the 7s, and 7 in the 5f. Right, so this has valence 5f electrons, right? So for the actinides, they are defined by valence 5f electrons, and the lanthanides are characterized by valence 4f electrons. All right. Okay. So, so that pretty much does our, overview of the periodic table with respect to valence electrons, right? Oh, I do want to point out here a little bit of oddness that happens here with copper and zinc, right? Well, let's focus on copper here, right? So if we look at the electron configuration for copper, you'll notice that this group is titled 1b, right? So something weird happens with the electron configuration of copper. If you're just writing it out, right, you might think that the electron configuration for copper, you'll just be like, okay, let's do argon, right? So you'll have argon, then you have 4s2, and then, here you got 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Might do 3d9. Right, so you might think, okay, well, copper has 9 valence electrons, right? So, or copper would have 11 valence electrons since you got 9 in the 3d and 2 in the 4s. This is actually incorrect. So what happens with copper is that because the 3d and the 4s are so close in energy, the electron, that one electron in the 4s is actually going to fill the 3d shell in order to make that stable 3d10 subshell. So you end up with the following electron configuration: 4s1, 3d10, right? So I know it looks kind of weird, but this is the correct electron configuration for copper. It's going to only have 1 valence electron in that 4s shell, rather than having that, partially filled d subshell. It's going to promote one of those electrons from the 4s to the 3d to fill that d shell to give you 1 valence electron in the 4s. And you can remember that just by looking at the periodic table. This group is titled 1b. So it must have 1 valence electron. That happens with copper, silver, gold, right? All of the ones in this row will promote that electron from the 4s to the 3d in order to get that filled 3d shell. Okay, so that's an overview of the periodic table from the standpoint of valence electrons. So in the next few videos, we're going to look at a few specific trends along the periodic tables, different properties that have trends along the periodic table that you can, use to infer which atom will have, for example, which atom will be larger, have a larger atomic radius, or which one will have a greater ionization energy. We'll talk about those properties and how their trends shake out on the periodic table.